This video presentation is brought to you by the Pro Mathematics Academy. Welcome to another video presentation brought to you by the Pro Mathematics Academy. In this presentation, we'll be looking at limits, right? And we'll be looking at the various types of questions that can be asked and various forms. All right, so here we have question number 1, which asks us to show that the limit as x approaches 0 of the modulus of x is equal to 0. So recall that the modulus of x is a piecewise function, right? Defined to be x if x is greater than 0, and it's negative x if x is less than 0. So I can take a look at that graph over here. We have our x-axis and our y-axis. We have that line which represents y equal x, and here we have this line which represents y equals negative x. So we see that the modulus function has those two parts and can be defined piecewisely. Now, to show that the limit as x approaches 0 of the modulus of x is 0, we have to show that the limit as x approaches 0 from the left of the modulus of x is equal to the limit as x approaches 0 from the right of the modulus of x, and both of these limits should be equal to 0. So now the limit as x approaches 0 from the left of the modulus of x is equal to the limit as x approaches 0 from the left of negative x. So where did I get negative x from? Well, we have to recognize that on the left side of this function, right, is y equals negative x. So if we're approaching from the left, we have to take that function, okay? And that's why we have the modulus of x being equal to negative x in this instance, which is equal to negative 0, which is 0, okay? Now we take the limit as x approaches 0 from the right of the modulus of x, which is equal to the limit as x approaches 0 of x, which is also equal to 0. Now notice that in this instance we were taking y equal x, which is the function that is on the right, okay? So in graphical form, we can observe, right, that this is the modulus of x function, but we can also represent the modulus of x through a piecewise definition. Okay, so either method can be used to aid in showing that the limit of this function as x approaches 0 is equal to 0. Okay, so I will put a concluding statement to say, since the limit as x approaches 0 from the left of the modulus of x is equal to 0, and the limit as x approaches 0 from the right of the modulus of x is also equal to 0. Therefore, the limit as x approaches 0 of the modulus of x is equal to 0. Okay, let's move to our next question. So for question number 2, we're asked to find this limit, okay? So we're trying to find the limit as x approaches 2 of x squared plus x minus 6 divided by x minus 2, okay? So we'll start by simplifying x squared plus x minus 6 over x minus 2, okay? And we'll recognize that we can factorize our numerator, right? So we can say x squared plus x minus 6 is equal to x plus 3 times x minus 2. Okay? So this means that the limit as x approaches 2 of x squared plus x minus 6 over x minus 2 is actually equal to the limit as x approaches 2 of x plus 3 times x minus 2 divided by x minus 2. And it's important for us to realize that we always want something to cancel from both our numerator and denominator. Okay? So here we have that. And so this simplifies to the limit as x approaches 2 of x plus 3. So therefore, I can now plug in x equals 2. So this then becomes 2 plus 3, which is equal to 5. It is important to recognize that we're actually taking our x plus 3 and we're evaluating this at x equals 2. Okay? So this is a mathematical notation, right? To tell us that we're taking the x plus 3 and we're plugging in x equal 2. And so we end up with that expression, which is equivalent. Moving right along to question number 3, we have the limit as x approaches minus 2, right, of x plus 2 divided by x cubed plus 8. Now, we need to simplify x plus 2 divided by x cubed plus 8. In order to do this, we need to factorize. What? Our denominator, which is x cubed plus 8. And to do this factorization, I'm going to do the division of polynomials, right? I'm going to do the division of polynomials. So here I have my x plus 2 and my x cubed plus 8. So the first thing I want to do is I want to ask myself, how many times does x go into x cubed, right? And that should be a simple, straightforward answer. It goes into x cubed, x squared times. Okay, that means we're asking ourselves, what is x cubed divided by x? And if we remember our laws of indexes, this should come out to be x squared. So now we ask ourselves, what is x squared times x plus 2? This is x cubed plus 2x squared. So this is the term that we'll now write down here, x cubed plus 2x squared. And we put that in our brackets and we subtract. This then becomes 0 and this becomes minus 2x squared. And we bring down our positive 8 from before. So now we ask ourselves, how many times does x go into negative 2x squared? So that's the same as asking ourselves, what is minus 2x squared divided by x? This then gives us minus 2x. So that means we have minus 2x right there. And so we now ask ourselves, what is minus 2x multiplied by x plus 2? This is equal to minus 2x squared minus 4x. Okay, so this means we can now write down minus 2x squared minus 4x in brackets. We're subtracting, so this becomes 0 and this becomes plus 4x. We still have our positive 8 carrying down. And lastly, we ask ourselves, what is 4x over x? That is simply 4. Okay, so I'm dividing this 4x by x, which is coming from here. So when I do that, I'll end up with 4. And now I want to take that same 4 and multiply by x plus 2. So that becomes 4x plus 8. And if I subtract in this final step, we realize we have 0, 0. So therefore, I'm missing my 4 right there. Therefore, I can conclude now that x cubed plus 8 is the same as x plus 2 times x squared minus 2x plus 4. Okay, so now we can go back to our limit, which is asking us the limit as x approaches negative 2 of x plus 2 divided by x cubed plus 8, right? We can now simplify this, or rather we can now insert the expression which we just derived. So this gives us the limit as x approaches minus 2 of x plus 2 all divided by x plus 2 times x squared minus 2x plus 4. Okay, and if we look closely here, we'll realize that something from our denominator and our numerator has canceled. So we're left with the limit as x approaches minus 2 of 1 over x squared minus 2x plus 4. And now we can say that this is the same as 1 divided by x squared minus 2x plus 4 evaluated at x equals negative 2. So this means we have 1 over minus 2 squared minus 2 times minus 2 plus 4, which is equal to 1 divided by 4 plus 4 plus 4, which is equal to 1 over 12. All right, so that's the answer here. Moving right along, we then go to question number 4. And for this one, we realize that the technique that we now have to implement does not involve factorization, but involves manipulating the expression by recognizing that we have a surd or a radical in our numerator. So we need to simplify. Okay, so now we have the square root of x plus 2 minus 3 divided by x minus 7. And what I want to do is to take my conjugate of my numerator. Okay, yes, that's right. I want to take the conjugate of my numerator. And I want to multiply my numerator by its conjugate and multiply the denominator by the conjugate as well. And this is a generalized technique that we use to simplify surds. Okay, so here this becomes the square root of x plus 2 plus 3 divided by the square root of x plus 2 plus 3, right? And we realize that when we multiply these two terms in the numerator together, we end up with the difference of two squares, okay? Whenever we multiply these two terms in our numerator together, we end up with the difference of two squares. So here this becomes the square root of x plus 2 squared minus 3 squared, all divided by x minus 7 in bracket times the square root of x plus 2 plus 3 in bracket. Okay, simplifying. Whenever we square a square root, we end up with the original expression because the square root cancels the square. And we're subtracting 9 here and dividing by x minus 7 in bracket times the square root of x plus 2 plus 3. In our numerator, we realize now we have x minus 7, and we're also dividing by x minus 7. So then this becomes this gives us something that can be cancelled from both denominator and numerator. So now we're left with 1 over the square root of x plus 2 plus 3. Okay? Nice. So, what do we do now? We go back to our limit as x approaches 7, right, of the square root of x plus 2 minus 3 over x minus 7. And what we realize now is that this can be simplified into the limit as x approaches 7 of 1 over the square root of x plus 2 plus 3, which now is basically evaluating this term at x equals 7. So what we end up with is 1 over the square root of 7 plus 2 plus 3, which is equal to 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is equal to 1 over 6. And that is our final answer. Okay, moving right along. Our next question asks us to find the limit as t approaches 0 of the reciprocal of t times the square root of 1 plus t minus the reciprocal of t. So now let's simplify 1 over t times the square root of 1 plus t minus 1 over t. So here we're looking for the LCM of t times the square root of 1 plus t and t. Okay, so in this case, the LCM of these two equals t times the square root of 1 plus t. Okay, that's what the LCM is. Take some time to think about it, but it should be straightforward after thinking about it. Now, this means that we can write the limit. Well, let's not go to our limit yet. We can write 1 over t times the square root of 1 plus t minus 1 over t as 1 take away the square root of 1 plus t over t times the square root of 1 plus t. Which now we'll ask ourselves, should we multiply by the conjugate of the denominator or should we multiply by the conjugate of the numerator? And because I am the mathematical expert here, I am going to tell you that what we need to multiply by is the conjugate of the numerator. Okay? So let's copy this down. Oh, we have that. And let's do one more copy. And one more copy. So what we're doing here is we're multiplying by the conjugate of the numerator, but I am multiplying both the denominator and the numerator by the conjugate. Okay? So now, this should simplify out to 1 minus the square root of 1 plus t squared, 1 plus the square root of 1 plus t squared, right? Because we have the difference of two squares there, divided by t times the square root of 1 plus t times 1 plus the square root of 1 plus t. Wow. Interesting. So simplifying our numerator gives us 1 minus 1 plus t, all divided by the same denominator we had before. I'm just going to copy this down. Okay. So now we see that we have negative t over the same denominator we had before, which then shows us that we can cancel something. What can I cancel here? Of course, I can cancel this t. Okay, so this means that we now have negative 1 over, not exactly the same thing before because this t is now canceled. Okay, so these two t's end up canceling each other, and now we're left with the expression below, which now we can go back to our limit to say that the limit as t approaches 0 of 1 over t times the square root of 1 plus t minus 1 over t is equal to the limit as t approaches 0 of negative 1 over the square root of 1 plus t times 1 plus the square root of 1 plus t. Okay, which is equal to what? Negative 1 over the square root of 1 plus t times 1 plus the square root of 1 plus t evaluated at t equals 0, which is equal to negative 1 over the square root of 1 plus 0 times 1 plus the square root of 1 plus 0. And if I simplify all of this, I should get negative 1 over 2, which is equal to negative 0.5. Okay, and that is the answer. Now I know that that might have been a bit quick, so please be sure to pause the video sometimes and rewind if necessary in order to understand what was taking place at the given step. Okay, moving right along, and now we're going to go into question number 6. Question number 6, we have the limit as x approaches 0 of tan of ax divided by sine of bx, and of course a and b here are not equal to 0. Okay, now as per usual we need to simplify. Tan of ax over sine of bx, of course. So what is tan of ax? Tan of ax over sine of bx is actually equal to sine of ax over cosine of ax divided by sine of bx. So with that said, this can be simplified into sine of ax over cosine of ax multiplied by 1 over sine of bx, which is the same as sine of ax over sine of bx times 1 over cosine of ax. Now, what I'm going to do is I'm going to perform a necessary step here based on the property, the limit as x approaches 0 of sine x over x, right, is equal to 1. So if we're aware of this property, this might help us in what we're about to do. So by extending this property, we should be able to recognize that the limit as x approaches 0 of sine x, or sine ax, over ax is also equal to 1. Okay? So now, this was our side note. We'll make a note of that. So now, we can go back to our limit. The limit as x approaches 0 of tan of ax over sine of bx is equal to the limit as x approaches 0 of this expression that we just found. Wow, so after simplifying, we're able to substitute the expression into another limit. Right, so this means I can take this limit as x approaches 0 of sine ax over ax in bracket, but where did that ax come from? Nowhere. So I have to multiply by ax in order to keep my expression true. Now I divide by sine bx over bx, but where did that bx come from? Nowhere. So I also multiply by bx on the outside, which keeps our expression true. Likewise, I am multiplying by 1 over cosine of ax, which this now means that I can use the limit property, right? I can use the limit property, which says that the limit can be distributed over functions, right? This might be a lot of writing, so I'm just gonna copy and make the adjustments. Right, so this allows us to distribute this limit over each of these terms. Okay? So distributing the limit then gives us let's write these in first. Okay, so what we did there is to apply the limit to the numerator, apply the limit to the denominator, right? And apply the limit as a product. Okay, what limit law am I quoting? Somebody's wondering. This is saying that the limit as x approaches some a of f of x times g of x, right, is equal to the limit as x approaches a of f of x times, see, I'm running out of space here, times what? The limit as x approaches a of g of x, that's for products, and for quotients, we have the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, given that, right, the limit as x approaches a of g of x is not 0. Okay, so these are the limit laws I'm using. So basically, whenever we have the limit being applied to a quotient or product, we can distribute the limit over the quotient and over the product. Okay, so that means here we have 3 different limits to evaluate. So continuing with our question, we now have these 2 x's will cancel each other. The x in multiplying the ax and the x multiplying the bx will both cancel each other. So we'll be left with 1 times a divided by 1 times b, right? Because this limit, let me see if I can find a different color. This limit turns out to be 1, as we already said, and this limit also turns out to be 1. And so we end up with 1 and 1. Multiplying the limit as x approaches 0 of 1 over cosine of ax. But this limit is also equal to 1. Okay? The limit as x approaches 0 of the reciprocal of cos x is also 1. Okay, so this is equal to a over b multiplied by 1, which is equal to a over b, our final answer. Okay, this one was a bit complicated, but the principles are to be followed for any method for which you're going to use to find this limit. Okay, moving right along, we're at question number 7, right? And for this one, we have to simplify somewhat as per usual. So we need to, it seems we always need to simplify. Well, simplifying is always our best bet. So simplifying here, we want to simplify this quotient sine x over the square root of x. But what do we actually need? We want sine x over x. Okay, but do we have that? No. So multiply both numerator and denominator by square root of x. This means that sine x over the square root of x times, well, I'm going to say that this is equal to sine x divided by the square root of x times the square root of x over the square root of x, right? Which is equal to sine x over x times the square root of x. So now the limit as x approaches 0 from the right of sine x over the square root of x is equal to the limit as x approaches 0 from the right of sine x over x times the square root of x. And yes, you guys guessed it, I'm going to apply my limit law again. So this is going to be the limit as x approaches 0 from the right of sine x over x times the limit as x approaches 0 from the right of the square root of x. Okay, so here this one becomes 1 because I already gave you that definition, and I'm multiplying this by 0. So therefore 1 times 0 is equal to 0. Okay, nice. Let's move on to question number 8. And I know by now everyone is thinking that we need to simplify, and that is correct. So here we have 3x minus sine kx, and I'm dividing that by x. So now this expression is equal to 3x over x minus sine kx over x, which is equal to 3 minus sine kx over x. Now, we do not have a kx in the denominator, but we want to have a kx in the denominator. Okay, but where did that k come from? Nowhere. So we have to multiply by k in order to keep our expression true. Okay, so this then means that the limit as x approaches 0, right, of 3x minus sine kx over x is equal to the limit as x approaches 0 of 3 minus sine kx over kx times k. So this then means we have the limit. That's right, I'm going to distribute my limit over my expression. So this is limit as x approaches 0 of 3 minus the limit as x approaches 0 of sine kx over kx times k, which is equal to 3 minus, because the limit of a constant is equal to that same constant. So here the constant is 3. So if I take the limit of 3, then I end up with 3. Here this becomes 1 multiplied by k, because once we have sine of x or sine of f of x over f of x, right, then the limit of that function turns out to be 1. So therefore our final answer is 3 minus k. Okay, so remember guys, feel free to pause the video at any point, rewind, and go back to the necessary step in order to understand. Okay, also feel free to comment down below if there was anything that you thought could have been done differently. Okay, all right, so that's it for this presentation. That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.